Okay, for starters, I want to make sure everything in this problem is in MKS units. So I'm going to convert 44 miles per hour into meters per second. Do that by multiplying by 1 hour or 3,600 seconds, and 1,609 meters over 1 mile. That leaves me with 19.67 meters per second for the car's final velocity in part 1. And you can see from the problem statement that there are two distinct parts to the problem. Right, our equations of motion are for constant acceleration. There are two parts to the problem with constant acceleration. There's the first part, where she's accelerating uniformly from rest, and then the second part where her acceleration is -1. So, let's write down what we know for each part. Okay, if you haven't already done this and written down what you're assuming and what you don't know, then you should pause the video and fill in these two tables with everything you can before we go forward. Okay, so I'm going to start with part 1. We don't know the displacement. Starts from rest, reaches a final speed of 19.67 meters per second. Acceleration is not given. The time is 8.0 seconds. Now, I don't think we're going to need the acceleration for anything, but we are going to need delta x. So I'll use the equation that doesn't have the acceleration in it, which is delta x is 1/2 e plus v naught t. So that's 1/2 times 19.67 plus 0 times 8.0. And that works out to be 78.67 meters. For part 2, again, we don't know delta x. We know that the initial velocity for part 2 is the final velocity from part 1. Right, that's pretty typical. And the acceleration lasts until the car stops, so the final velocity will be 0, and acceleration is -1 meter per second squared. Notice in the problem statement I gave the acceleration as a magnitude and a direction. Gave you the magnitude as 1.0, and I said the direction is opposite the motion. And since the velocity is positive, we've got a sign convention here that the direction of motion is positive. So the acceleration points opposite the direction of motion, so it must be negative. Okay, so for part 2, I need to find delta x2 and t2. So to find delta x2, I'll use the equation that doesn't have t in it. That's v squared is equal to v naught squared plus 2a delta x, and that is 0 squared is equal to 19.67 squared plus 2 times -1 times delta x, and that works out to be delta x is 193.45. That's delta x2. Up here is delta x1. So we've got our displacements. And I'm also going to need t2, so I'll use the equation that doesn't have x2 in it, and that's v2 is v naught 2 plus at, or 0 is equal to 19.67 plus -1 times t. So t is 19.67 seconds, t2. Alright, now this asks for the average velocity for the whole trip. You might be tempted to say, well, the average velocity is 1/2 times the average velocity from part 1 plus the average velocity for part 2 or something like that, and you really can't do that. The only equation that we have for average velocity is that it's related to the displacement, right, with this. That's one that always holds. This business of average velocity being equal to 1/2 times v plus v naught, and we sometimes see that's only good when the acceleration is constant. But the acceleration is not constant throughout this problem. You've got up here, there's some acceleration which we don't know, and down here is an acceleration -1. So we can't use that. So we have to use this. We have to say that v bar total for the total trip is equal to the total displacement divided by the total time. That's our only option. And the total displacement is delta x1 plus delta x2. The total time is t1 plus t2. Right? So that's 78.67 plus 193.45 divided by the time, which is 8.0 plus 19.67. So that works out to be 9.8 meters per second. And that's sufficient for your answer. If you wanted to convert it back into miles per hour, it would be 22 miles per hour.